So I was talking to this chatbot yesterday and I asked it to help me with a complex math problem. It gave me this super confident answer that was completely wrong.
Classic AI hallucination. You know what would be amazing? If these models could actually tell us when they're about to make a mistake.
Like some kind of AI self awareness? That would be game changing.
Well, funny you should mention that.
Welcome to another episode of Totally Unprofessional Peer Review. I'm Casey Park, your developer host who's obsessed with structure and flow.
And I'm Max Stone, your friendly neighborhood theorist who can't stop thinking about metrics and methodology.
Today, we're diving into a fascinating paper that tackles one of the biggest problems with large language models: their inability to recognize when they're wrong.
The paper is called "Can LLMs Predict Their Own Failures?" Self-awareness via internal circuits, and introduces something called Gnosis, which is a lightweight mechanism that allows frozen language models to verify their own outputs.
What's really cool about this approach is that instead of relying on external judges or generating multiple answers to check consistency, Gnosis looks at the model's own internal states during inference.
Right, it's like giving the model a mirror to look at its own thought process. And apparently, it works across different types of tasks like math reasoning, open domain questions, and academic knowledge.
And get this, it only adds about 5 million parameters, which is practically nothing compared to the billions in these large models.
So, we're talking about models that can essentially raise their hand and say, I think I might be wrong here, without any extra computational heavy lifting.
Exactly. And imagine what this means for practical applications. We could potentially stop hallucinations before they even happen.
It's like giving AI a built-in lie detector test that it administers to itself.
In today's episode, we'll break down how this self-awareness mechanism works, look at the practical applications, and discuss what this means for the future of AI reliability.
And stick around to find out if we can finally trust our AI assistants to know when they're just making stuff up. Spoiler alert, the answer might surprise you.
So let's dig into this self-awareness problem. Why is it so difficult for large language models to know when they're wrong?
It's actually one of the most fundamental challenges in AI right now. These models can generate incredibly fluent and complex outputs, but they have a major blind spot. They often can't tell when they're making things up.
Right, and that's what the paper calls the gap between strong generation and weak self-verification. It's like they can talk the talk, but they can't check if what they're saying makes any sense.
Exactly. And this isn't just an academic problem. It seriously limits how reliable and safe these models can be in real-world applications, especially when they need to perform complex reasoning tasks.
So, before Gnosis came along, what were the main approaches to solving this problem?
The paper outlines three main approaches that have been tried. First, there's text-based self-critique, where the model is basically asked to review its own answer.
Like asking, "Are you sure about that?" after it gives an answer.
Pretty much. The problem is that these approaches tend to track linguistic fluency rather than actual reasoning validity. So a model might be very confident about a completely wrong answer just because it sounds good.
That's like asking someone who's confidently wrong to check their own work. They'll probably just double down on being wrong.
Then there's the multi-sample consistency approach, where you ask the model to generate multiple answers to the same question and see if they agree.
That makes sense. If the model gives different answers each time, it's probably guessing.
Right, but there's a big downside: computational cost. The inference cost scales linearly with the number of samples you generate. So if you want to be really sure, you might need to generate 5 or 10 answers, which multiplies your computing costs.
And the third approach?
External judges, or reward models. Basically, you train a separate AI model whose job is to evaluate the answers from your main model.
So it's like having a second opinion from another AI.
Exactly. These can provide strong signals about correctness, but they come with their own costs. You need substantial annotation to train them. They add inference latency because you need to run a whole separate model, and they require additional compute resources.
Let's look at some data from the paper. They compared different methods for detecting when models are wrong across different domains.
This table is really telling. It shows how different methods perform at detecting when models are hallucinating or making mistakes. Look at the math reasoning domain at the top. You can see traditional methods like logit entropy and mean token probability have decent performance, but they're not great.
And the external judge models like Skywork RM and Gemini 2.5 Pro do better. But then, Gnosis, their new approach, outperforms all of them. Those numbers in bold at the bottom of each section show it's consistently better.
What's really impressive is that this pattern holds across different types of tasks: math reasoning, open domain question answering, and academic knowledge. Gnosis is consistently at or near the top in performance.
And it's doing this without the computational overhead of generating multiple samples or running a separate judge model.
That's the breakthrough here. Instead of these external approaches, Gnosis is looking at the model's own internal states during generation, its hidden states and attention patterns.
So it's like the model is monitoring its own thought process in real time.
Exactly. The paper shows that there are reliable signals about correctness embedded in how the model processes information internally. When a model is about to hallucinate or make a mistake, there are patterns in its internal activations that can be detected.
That's fascinating. So instead of asking the model, "Are you sure?" after it's already given an answer, Gnosis is watching how the model arrives at that answer in the first place.
Right. And what's really interesting is that these signals aren't just at the final output layer, they're distributed throughout the network, with middle and deep layers containing particularly strong indicators of whether the model is on the right track.
It's almost like the model knows it's making things up, but that information just wasn't being captured before.
That's a great way to put it. And the most impressive part is how lightweight this approach is. Just 5 million additional parameters to extract these signals, which is tiny compared to the billions in the base models.
So, to summarize the challenge, LLMs are great at generating content, but terrible at self-checking. Existing solutions either don't work well or cost too much computationally. And the key insight of this paper is that models actually contain internal signals that can tell us when they're about to be wrong.
That's it in a nutshell. The self-awareness is already there in the model's internal circuitry. We just needed a better way to access it.
So now that we understand the problem, let's dig into how Gnosis actually works. I'm really curious about the technical details here.
Let's look at this diagram from the paper that shows the architecture. It's pretty elegant when you break it down.
So what we're seeing here is how Gnosis taps into the model's internal states while it's generating text. It's basically observing two separate streams of information.
Exactly. The top stream is extracting information from the hidden states. Those are the internal representations that the model builds as it processes text. And the bottom stream is looking at the attention maps, how the model is focusing on different parts of the input and its own generation.
And then both of these streams feed into what they call a judgment head that outputs a correctness score between 0 and 1.
Right. What's really clever about this approach is that it's completely passive. Gnosis isn't changing how the model generates text, it's just observing the process and looking for patterns that correlate with correctness or hallucination.
So it's like having a lie detector that's watching the model's brain activity as it thinks.
That's a great analogy. And just like how a polygraph measures multiple physiological signals, Gnosis is looking at multiple internal signals from different parts of the model.
Let's break down these two streams in more detail. What exactly is the hidden circuit encoder doing?
The paper goes into quite a bit of detail on this. Let me show you a more detailed diagram of the architecture.
Wow, there's a lot going on here. So on the left, we have the hidden circuit encoder, which is processing those hidden states.
Right. The key challenge they're solving here is that the hidden states vary in length depending on how long the generated text is. So first, they project these states to a fixed dimension. Then they use something called adaptive average pooling to compress the sequence.
And then they apply these multi-scale dilated convolutions. What's that about?
That's capturing temporal patterns at different scales. Think of it as looking for both local patterns, like how the model transitions between adjacent tokens, and broader patterns across the whole generation.
And then they use attention mechanisms to further compress all this information into a fixed size descriptor. So no matter how long the text is, they end up with the same size representation.
Exactly. And on the right side, we have the attention circuit encoder, which is doing something similar but with the attention maps.
I see they're using both statistical features and a CNN, a convolutional neural network, to analyze the attention patterns. Why both approaches?
The paper mentions they're complementary. The CNN is good at capturing visual patterns in the attention maps, like whether attention is focused or scattered. The statistical features capture things like how concentrated the attention is, or how local versus long range it is.
So they're treating each attention map almost like an image and analyzing its patterns. That's pretty clever.
And what's interesting is that they found both streams contribute useful information, but in different ways for different tasks. For factual questions, the hidden states carry most of the signal. For complex reasoning, the attention patterns become more important.
That makes sense. When you're just recalling a fact, the confidence is probably encoded in the hidden states. But when you're working through a complex math problem, how you're connecting different parts of the reasoning chain, which is what attention shows, becomes really important.
Exactly. And then the final step is to fuse these two streams. They concatenate the two descriptors and feed them into what they call a gated MLP, essentially a small neural network that can adaptively weight the importance of the hidden versus attention features for each specific example.
And all of this adds up to just 5 million parameters? That seems tiny compared to the billions in the base models.
That's one of the most impressive parts. The paper says it's about 1,000 times smaller than an 8 billion parameter reward model, and because it's just observing the model's internal states during normal generation, there's essentially no added inference cost.
Let's look at some visualizations of what Gnosis is learning. The paper has some really interesting figures showing how it separates correct from incorrect answers.
This figure is fascinating. It shows 2D embeddings of the features that Gnosis learns for math reasoning tasks. The red points are wrong answers, and the blue points are correct answers.
So on the left, we see the hidden state features, which show a pretty clear separation between correct and incorrect answers. The middle shows the attention features, which also show separation, but it's not quite as clean. And on the right, we have the merged features, which give the sharpest discrimination.
This really supports their claim that both streams contain useful information about correctness, and combining them gives the best results. It's like the model is leaving fingerprints of its confidence and accuracy in these internal patterns.
Another cool aspect of Gnosis is that it can predict correctness even before the model finishes generating an answer. Let's look at that chart.
This is showing how well different methods can predict whether an answer will be correct after seeing only a fraction of the generation. The red line is Gnosis, blue is a baseline method using token probabilities, and yellow is a reward model.
And Gnosis is consistently better at every stage. Even after seeing just 40% of the answer, it's already performing better than the other methods do with the complete answer.
This early prediction capability is really powerful. It means you could potentially stop a model mid-generation if it starts going down a wrong path, saving compute and preventing hallucinations before they're even fully formed.
So to summarize how Gnosis works, it's a lightweight mechanism that observes the model's internal states and attention patterns during generation, compresses them into fixed-size descriptors, and uses these to predict whether the output is correct, all with minimal computational overhead.
And what's really groundbreaking is that it shows these models already contain internal signals about their own correctness. We just needed a way to access and interpret those signals. It's not adding any new reasoning capabilities to the model, it's just making explicit what was already implicitly there.
It's like the model knows when it's making things up, but that information was getting lost in the final output. Gnosis is giving the model a way to communicate its own uncertainty.
Exactly. And the fact that it works across different model sizes and different types of tasks suggests this is a pretty fundamental property of how these models work, not just a quirk of a particular architecture.
One last thing I found interesting is how they trained Gnosis. They didn't need any special annotations, they just generated answers with the base model, compared them to ground truth answers to determine correctness, and trained Gnosis to predict that binary label.
Right. And because the backbone model stays frozen and all the feature extractors operate at a fixed budget regardless of sequence length, the training is really lightweight. The paper mentions that even for the largest 20B parameter model, the whole pipeline finished in about 12 hours on two A100 GPUs.
That's impressive efficiency. So now that we understand how Gnosis works under the hood, let's talk about what this means for practical applications and the future of AI reliability.
Now that we understand how Gnosis works, let's talk about the practical applications. This isn't just an academic exercise, the paper points to some really exciting real-world uses.
Absolutely. The first big application is obviously more reliable AI systems. If models can accurately flag when they're likely to be wrong, we could dramatically reduce hallucinations in production systems.
Right, and what's impressive is how little overhead this adds. Let's look at this table from the paper that compares the latency of Gnosis versus a traditional reward model approach.
This is pretty striking. For a 12,000 token response, the Skywork RM reward model takes 930 milliseconds to judge correctness, while Gnosis takes just 25 milliseconds. That's 37 times faster.
And it gets even more dramatic with longer outputs. For 24,000 token responses, the reward model takes almost 2.5 seconds, while Gnosis still only needs 25 milliseconds, a 99x speedup.
What's really interesting is that Gnosis maintains constant latency regardless of the sequence length. That's because it's compressing all those internal states into fixed size descriptors.
And look at the ROC scores. Gnosis is actually more accurate too. So it's not just faster, it's better at detecting when the model is wrong.
Another practical application that I found fascinating is what they call early correctness prediction. Basically, Gnosis can tell if a model is going to be wrong before it even finishes generating its answer.
That's a game changer for efficiency. The paper mentions that after seeing just 40% of a model's generation, Gnosis can already predict correctness as accurately as other methods can with the complete answer.
Think about what that means in practice. If you can tell that a model is heading down the wrong path early on, you could stop the generation, saving compute resources and preventing the model from fully developing an incorrect answer.
Or you could implement what the paper calls compute-aware control. If the model detects it's likely to fail on a given question, it could automatically escalate to a more powerful model that might handle it better.
That's like having a junior employee who knows when to ask for help from a senior colleague instead of just guessing. It's a much more efficient use of resources.
Another application that surprised me was what they call sibling modeling. Let's take a look at this table from the paper.
So what we're seeing here is that they trained a Gnosis head on a small 1.7b parameter model and then used that same head to judge outputs from larger 4b and 8b parameter models without any additional training.
And surprisingly, it works really well. Look at the math domain at the top. The Gnosis head trained on the 1.7b model achieves AUROC scores of 0.93, 0.97, and 0.7b, 4b, and 8b models respectively.
That's actually better than the dedicated Skywork RM reward model in some cases. And we see similar results for the other domains too, open domain QA and academic knowledge reasoning.
The paper calls this a free lunch. You can train one small Gnosis head on your smallest model and then use it to judge outputs from your entire model family. That's incredibly efficient from a training and deployment perspective.
It also suggests something really interesting about how hallucinations work. The paper mentions that this transferability implies that hallucination manifests as a structural invariant across model scales.
In other words, the patterns that indicate when a model is about to hallucinate look similar, whether it's a small model or a large one. That's a fascinating insight into how these models work.
Let's take another look at that main architecture diagram, because I think it helps illustrate why this approach is so versatile.
Right, so Gnosis is essentially this passive observer that's watching the model think. It's not changing how the model generates text, it's just monitoring the process and looking for signs of trouble.
And because it's looking at these fundamental patterns in hidden states and attention maps, those patterns seem to be consistent across different model sizes and even different types of tasks.
Let's talk about the broader implications. One thing that jumps out to me is that this approach could significantly reduce the cost of deploying reliable AI systems.
Absolutely. Right now, many companies are using expensive techniques like generating multiple answers and comparing them, or running separate verification models. Gnosis could potentially replace all of that with a tiny add-on to the base model.
And it's not just about cost, it's also about accessibility. If reliable self-verification can be achieved with such minimal overhead, it becomes much easier to deploy trustworthy AI systems in resource-constrained environments, like on edge devices or in applications where latency is critical.
I'm also thinking about what this means for AI safety. If models can reliably detect when they're about to make a mistake, that creates an additional safety layer. The model could refuse to answer questions it's likely to get wrong, or at least flag its uncertainty to the user.
That's a great point, and it could potentially help with the problem of overconfident wrong answers, which is one of the most concerning aspects of current AI systems.
I think there's also an interesting philosophical angle here. The fact that these models already contain internal signals about their own correctness suggests a kind of proto self awareness that we hadn't fully appreciated before.
It's like they have an implicit understanding of their own knowledge boundaries, but that understanding wasn't being surfaced in their outputs. Gnosis is making that implicit knowledge explicit.
One limitation I see is that Gnosis is still a binary classifier. It's predicting whether an answer is correct or not. It's not providing nuanced explanations of why it thinks an answer might be wrong.
That's true, though I could imagine future work that extends this approach to not just detect errors but explain them, maybe by analyzing which parts of the internal states contributed most to the error prediction.
Another thing to consider is how this approach might generalize to other types of models beyond language models. Could similar techniques be applied to multimodal models that handle images and text, or to reinforcement learning agents?
That's an interesting question. The core idea that models contain internal signals about their own performance might well apply across different architectures. We might just need different ways of extracting and interpreting those signals.
To sum up the practical implications, Gnosis offers a way to make AI systems more reliable with minimal computational overhead, enables early detection of errors to save compute resources, and provides a unified approach to verification across model scales.
And it does all this by tapping into signals that were already present in these models but weren't being utilized. It's like finding a built-in error detection system that was there all along, but nobody had figured out how to access.
I think that's what makes this work so elegant. It's not adding complex new capabilities to these models, it's just making better use of what they already know about themselves.
And if this approach continues to prove effective across different models and tasks, it could become a standard component of AI systems, a lightweight add-on that dramatically improves reliability without significant cost or complexity.
That would be a major step toward AI systems we can actually trust, which is something we desperately need as these technologies become more prevalent in our daily lives.
Absolutely. The gap between fluent generation and reliable self-verification has been one of the biggest challenges in AI safety. Approaches like Gnosis suggest that gap might be narrower than we thought. So there you have it, a fascinating look at how AI models might finally be able to know when they're wrong. What stands out to me is how elegant this solution is. The self-awareness was there all along, hiding in the model's internal circuits.
Absolutely. And with minimal computational overhead, this could be a game changer for AI reliability in real world applications. I'm excited to see how this technology develops and gets implemented across different systems.
Until next time, this is Max Stone.
And Casey Park signing off from Totally Unprofessional Peer Review. Remember to like, subscribe, and leave us a comment.
And hey, unlike our AI friends, if we said anything wrong today, at least we can blame it on being human.